foundational, it's fundamental stuff really, but I think a lot of times we gloss over it, right? But it's important to take the time to do that stuff. So we're doing that, atomic structure. So I'll be doing that with you guys today. We're doing radioactivity. Then we'll go into like atomic orbitals and shells and this whole idea of these different energy levels and how you feel these energy levels. Your electronic configuration is going to be a little bit different than what you were taught in CXC, right? So I'm going to teach that today. And then of course unit 2, you're not really concerned with unit 2 stuff right now because that's above your level now. You just want to master what you're mastering here with unit 1. So let's focus on that. So let's see, it's 4:41. So I'm gonna go ahead and share my screen here with what I have prepared for you. So let's see. Share my screen. This is my PowerPoint. Okay, yeah, so this is where we stopped last time. So Shinella, you're saying that today is your first time here. I hope you were able to watch the video that we have on YouTube from last week. So you're like not completely lost here. Were you able to watch that, Shinella, the video on YouTube?
No, I didn't get a chance to watch it.
Okay, I don't think you'll be too lost with what we're doing here. You've probably seen this stuff already, have you? With alpha decay, beta decay, and gamma decay?
Yes, I've seen something similar to this.
Okay, great. And Beyonce, do you remember what we were talking about last time with the alpha decay and how you write the equation for the alpha decay? Okay, so Beyonce says she remembers. Okay, I'm just gonna recap it. So to start here for today, with the equations for radioactive decay. So we mentioned last time that there are 3 types of products of radioactive decay, right? And these are alpha particles, beta particles, and gamma rays, right? And so in the alpha decay, where you're actually the particle that you have these radioactive, you have these isotopes, right? And then there are levels to isotopes, and the level up is a radioactive isotope. And a radioactive isotope just means that the nuclei or the nucleus of that isotope is very unstable. And so it will spontaneously disintegrate. It will just break down into pieces, right? And some of the pieces that you then get are what I mentioned earlier, those alpha particles, beta particles, and those gamma particles, right? All right, so the alpha particle in particular, scientists, chemists, the physicists, the people who study these things have likened the alpha particle or alpha decay to the liberation of a helium nuclei, right? A particle, some particles that are similar in how they are in structure and nature to a helium nuclei, right? And so when we have a decay of a radioactive isotope then that undergoes alpha decay, we're gonna get a helium nuclei that evolves as a result of that, and we're also gonna get a smaller element, for lack of a better word, a smaller element. So let me just show you what that looks like as far as alpha decay goes. So we're a fairly tight group today, so definitely feel free to communicate with me and stop me if you have any questions, okay? And raise your hand if you have any question. Give me a thumbs up and let me know if it sounds good, if it's making sense, or if it's not, because we're a fairly tight group today, okay? And even if we weren't a tight group, I always encourage students to ask me whatever their question is so that nobody is here lost. It doesn't make sense for us to be doing these very special and tailored, sessions for you students and you still don't understand, right? The goal is for you to walk away having an understanding that you didn't have otherwise, and that this is beneficial to you. So if you have any questions, feel free to ask me. Okay, so now I'm writing the equation of radioactive decays. The first one we're going to write is the decay, is a product when the decay product is an alpha particle, right? So, okay, so we have a product, so we have an element radium, right, is what we did last time for alpha decay. So let's write that out. So alpha decay, we have our 2, 2, 3, that's our mass number of radium, right? And our atomic number is 88, and that this is just the symbol of that element radium, right? When this element or this radioactive isotope undergoes a decay, alpha decay, what we're gonna get then, because the alpha particle, as I mentioned earlier, we liken that to a helium nuclei, which is just this, right? It's helium here, right? So as I said, when you undergo alpha decay, you're gonna give off, for lack of a better word, a helium nuclei. And if I'm starting here with radium, right, and I'm giving this off, what's gonna be the new mass then? How is this mass number and atomic number gonna be affected by this change in the nuclei? Anybody want to tell me what's gonna happen to my mass number and my atomic number as a result of this kind of a decay? So I'll start us off here. We're gonna give off this helium nuclei. So that's one, that's a starting point, right? And then what's gonna happen as far as our element or new element of interest here goes? Beyonce, do you remember this from last time? I'm picking on you because you were here. So let me know. Beyonce, feel free to unmute yourself and let me know. So just shout that out for me, Beyonce. What's gonna happen from a mass number standpoint and an atomic number standpoint to radium, okay? So what change is it gonna undergo?
Miss, the atomic number will lose 4, so it will be 219. And the mass number will lose 2, so it will be 886.
I think it's correct, but you flip what the numbers actually are. So say it again. The mass number, which is the larger of the two, is what's gonna happen to that?
Miss, the mass number will lose 4 and will be 219.
Okay.
And then the atomic number will lose 2 and be 86.
Okay. So do you follow that, Shanella? And then we're gonna get what we call radon, I think is what this element is, Rn, right? So is that clear to you, Shanella? Does that make sense? Is that because we're undergoing alpha decay and we're essentially losing a helium nuclei, we're gonna be minimized, the mass number and the atomic number is gonna be reduced by this amount. Okay?
Yes, miss.
Okay, so that is for alpha decay. So make sure that you're clear on that, because this could be one of the very first questions you see on the exam. It's very likely, okay? So then now, let's talk about beta decay. Does anybody remember what we liken beta particles to? Like, what do we typically say it's equivalent to, more or less? A beta particle is like a, or like an, what is a beta particle like? Anybody? What's a beta particle like? You know how we said the alpha particles? Go ahead. Is that somebody speaking?
Miss, I was asking if it was the electron.
Exactly. So it's like an electron. That's what we liken these beta particles to. So then if I'm supposed to write it, then I would write, not that. That's a little bit too thick, but let me show you how we would represent symbolically, how we would represent an electron. So let me. Okay, so if we're representing an electron, we'd represent it like this. You say 0. Oh, my, that line is very thin. Let me fix that. So it's a 0 minus 1 E, right? That's how we represent an electron. Just as how we write the helium nuclei up here, we write the electron like this, right? So that's how we would do that. So that's a beta decay. Now, if a radioactive isotope undergoes beta decay, right? Let me write down an example and we're gonna get to it eventually. But if so carbon 14, which we spoke about last time, as something that we use, a radioactive isotope that we use in carbon dating, it undergoes beta decay, right? And you're gonna see something really cool once we get to that particular equation. But just be thinking about this here for a minute with me, right? If I'm saying that in the previous case where we're doing alpha decay, we are losing a helium nuclei. And so we have a reduction of our mass number and a reduction of our atomic number, right? By 4, 2He. So that's what we have here. That's what I've written here, right? For the beta decay, we are saying that beta particles are like electrons. We are likening them to electrons. And we are saying that you're losing this carbon 14 that I have at the bottom of the screen is losing an electron essentially, right? So if it's losing an electron, what might happen? What do you think would happen from a mass number and an atomic number standpoint? And no wrong answers here. Just let me know what you want. No, just throw them out and then we can work through it, okay? So let me know, what do you think would happen from a mass number and an atomic number standpoint? Know that we're like losing an electron-like particle. Anybody wants to take a guess? An educated guess as to what would happen? Let me see. Beyonce says, Miss, the mass number will remain the same number as before. Okay, and how do you get that? Why? And the atomic number will change, says Shinella. Okay, so they're like working in tandem now. How will the atomic number change, Shinella? What will happen to it? What do you think will happen to it?
This based on the equation that I see here representing the decay, like the one. So I was thinking of that.
So what would happen? Wait, how would the atomic number change? It would lose one or it would gain one?
It will lose one.
It would lose one? Okay, I see where you're going with it, but I'm going to show you what actually happens, right? Or how it is that the scientists have been able to rationalize this this change that happens where you're getting an alpha-like, or you're getting an electron-like particle, right? So the thing that's interesting about these kinds of decay, when we talk about radioactive decay and how that kind of a decay is largely caused by an unstable nuclei, right? So the nucleus, the center of the atom, is when that's unstable, when you have an isotope that's unstable there from a nuclear standpoint, that's when you have radioactive decay. It's a spontaneous decay, right? So all of these things is a nuclear phenomenon. And by that, I mean that the changes that are happening in the nucleus, and in the nucleus, you have the proton and the neutrons, right? No, there are no electrons in the nucleus, if you think about it, right? Because where do we find electrons? The idea that we can have an electron-like particle that's coming out as a result of radioactive decay is very interesting. It was very interesting and very fascinating to me to think about. And so okay, so let's back up a little bit. Where are electrons found? Where are we taught that electrons are in the grand scheme of an atom? Where are electrons found? And definitely feel free to unmute and talk to me. You don't have to be in the chat, okay? You can unmute and talk to me and share that with me. Where are electrons found? Where are we taught that electrons are? When we think of the positioning of all our subatomic particles, right? When you think of your protons, you think of your neutrons, and you think of your electrons, we're generally taught that protons and neutrons reside in the nucleus, And then you have these electrons in what they call orbits or these shells that kind of orbit around the nucleus, right? So the idea that you could have a radioactive decay event that liberates an electron-like particle is very interesting. And so that's kind of where we are now, this beta decay stuff. Because what happens in beta decay, guys, is what they're saying is that you have a neutron, right, that gets transformed into a proton and an electron. Isn't that fascinating? Think about that for a little bit here. For beta decay, when you have these electron-like particles that are liberated, they are liberated. It's a nuclear phenomenon, and you have a neutron from the nucleus of that atom, of that isotope, that gets transformed to a proton and an electron. So I'm going to show you mathematically how they represent this. But just think about that for a little bit, guys. Sit with that for a little bit. We are taught that electrons are found in orbits around the nucleus, right? So the idea that you could get an electron from a neutron is mind-blowing. To me, it's mind-boggling. What do you guys think? I'm going to show you the mathematical representation of it. But this explanation is really interesting to me. It's really fascinating that you're getting an electron from a neutron. Like, what? How? You see what I'm saying? So I'm going to show you it mathematically, and then you will see what's going to happen to this carbon-14 when it undergoes a beta decay. Okay? So how does that sound to you guys? Let me know if you're like me in your amazement of the idea that you can get electrons from neutrons. Like, how? Talk to me, guys. Let me know what you're thinking about that whole concept. Sheila says, that's interesting. I want to show you the mathematical representation of it right now. So let me do that. Let me do that real quick. Give me a minute here, but just sit with that for a little bit. Just think of that we are saying that we have a neutron that gets converted into a proton and an electron, and that's where we get that electron-like particle in beta decay. Just sit with that for a minute. Let me get my screen going here, and I will write that mathematical representation for you, which is how you would actually write an equation that speaks to what I'm explaining happening here. Okay. So really, give me a minute, guys. But just think about that and feel free to talk to me about what you think about that while I get this squared away on my screen. Let me see. So I'm over there. I'm here. I'm here. I'm here. I'm here. I don't want to clear my screen because I don't want you guys to lose the contrast that I have going there. So let's see. I'm here. Okay. So we're ready again. We are ready to write. I'm going to show you the mathematical depiction of what's going on here. So as I said, the way that they've been able to describe this phenomenon whereby you get an electron out of a nuclear decay is that you have a neutron that gets converted into a proton and an electron, right? And mathematically, they write it as such. So let me show you how they write it. I'm here. I'm not drawing. Am I drawing? I'm not. I'm writing free-handed. Freehand drawing here. I see that Beyonce just joined us. Welcome, welcome, Beyonce. We're still on this.
Good evening.
Good evening. We're writing equations for radioactive decay. And I just shared with the group how you know, radioactive decay is a nuclear phenomenon largely. It's something that happened as a result of the nuclear spontaneously decaying. But then I was sharing with them how in beta decay, which is where we are now, in beta decay, what you have is an electron-like particle that you're getting. And I was saying, how fascinating is it that you're getting an electron out of the nucleus when we were taught in fundamental chemistry that electrons aren't found in the nucleus. They are found rotating around the nucleus in these shells, right? So isn't it fascinating then that you're getting electrons out of the nucleus, and how do you do that? And so I'm writing how that actually happens, okay? So how they've mathematically explained it is that you have a neutron that gets converted. So you have a neutron that's depicted as such. So the mass is 1. Remember that the mass of the neutron is 1. So that's that 1 right here. And this is your neutron, right? This is what we use to represent electrons. So that symbol here, that symbolic representation is of an electron. But down here now, I'm showing you how they mathematically describe this. You have a neutron, and what they're saying is that you have a neutron that gets converted into a proton, which is 1, 1, P. That's how we depict protons. It's kind of like a hydrogen atom, right? Remember, hydrogen is 1, 1. So we liken protons to hydrogens. And so that's how we would depict a proton, is 1, 1, P. And then now we also get an electron. So we are converting a neutron into a proton and an electron. And the electron is what I just wrote here. So that's 0, minus 1. That's minus 1, guys. Okay, this is a 1. This is a 1. Minus 1e. And that's our symbol for electron, right? And we're getting from our neutron 1 proton, 1 electron. So when you look at this mathematically, you see that it cancels out and you get back what's on the left, right? Do you guys see that? How you have your 1, 1p plus your 0 minus 1e is gonna get you what you started with, which is just 1, 0n. So that's your neutron. Are we all on that same page? Do we all see that, how that works out mathematically? That you have a conversion of neutron into protons and electrons. Is that clear?
Yes, ma'am.
Okay. All right. So in light of that fact, right, and that new knowledge that we now have, is that in beta decay, what's actually happening is that you're converting a neutron into a proton and an electron. In light of that fact, Beyonce and Trinella and Beyonce, what's gonna happen from a mass number standpoint? Let's start there. What's gonna happen to the mass number of this carbon-14 if it is that we have a neutron that's been transformed into a proton and an electron? Just think of it. Look at the equation that I wrote there and look at the carbon-14. If we have a carbon-14 that's essentially giving off, right, the neutron, a neutron from that carbon-14 is gonna convert into a proton and an electron. What's gonna happen from a mass number standpoint? The mass number is gonna stay the same, guys, because remember that the mass number is comprised of the proton and the neutron number. So it's just a conversion from one thing to another. We're converting a neutron to a proton. So it balances out, right? So think of it this way. I lose a neutron, I gain a proton. So -1 plus 1, it ends up being the same, right? So the mass number doesn't change. The mass number stays the same. Do we all follow that? Do we see that? How you're converting the neutron into a proton. So it's like you lose one, you gain one. It balances out, right? The mass number doesn't change. But from an atomic number standpoint, right? From an atomic number standpoint, What's gonna happen? What's gonna happen from an atomic number standpoint? Or a proton number standpoint?
Miss, will it be 7?
It would be 7. And how did you arrive there?
Miss, cause Miss, when I have the equation 0, -1 e, Miss, if Miss, I try to get back the 6 on the other side.
Exactly. So you're doing a math thing, right? You're doing a math thing. All right, so it would be 7, right? So it would be, but then no, Beyonce, look at this. What are we getting? What element are we gonna get? What element is that? And that's fascinating too in and of itself. Think about it. What element are we getting, Beyonce? What element is that? I'm gonna write it and you tell me. What element is this?
Miss Carver.
What's this one?
Never mind.
What element is that, Beyonce, that we're getting as a result of this beta decay?
Miss, is it nitrogen?
Exactly. So you see we get nitrogen from carbon? Think of that. Just think of that for a minute. Think of that for a minute, right? You have carbon and you get nitrogen. How that happen? How you get that from that? It is a result of this beta decay, where you have a conversion of that neutron into a proton and an electron, which from that, your mass number stays the same, but your atomic number, your proton number increases by 1. And from that increase, we end up getting a nitrogen atom, the element nitrogen. Do you guys see that? That's so fascinating, right? Think of it. Just think of that for a minute. All right, so let's move on to the next thing. But is that clear to you guys? Is that whole equation clear to you? I see that Anish has joined us. Welcome, Anish. Is this all making sense? Beyonce, I haven't heard you all evening. Is this all clear to you? Are you following?
Yes.
Yeah? Okay. All right, and Anish just joined us. So Anish, we're talking about these equations for radioactive decay. That's where we had left off last time. And we were talking about alpha decay. How in alpha decay, you have these particles that gets liberated, right? As a result of this unstable nuclei. When you have an alpha decay, a helium nuclei is what is liberated as a result of that disintegration. And so when you have a helium nuclei getting liberated from your isotope, there's a reduction of the mass number by 4 and the atomic number by 2, right? So that's how we're able to start with this radium element on the left and end up with radon and the 4He2, right? For beta decay, we're saying that beta decay is very fascinating, at least to me, because we're taught traditionally that electrons are found in these shells that orbit the nuclei, right? But radioactive decay is it's a nuclear phenomenon. So how is it that we're able to get electron-like particles from a nuclear decay? How are you getting electrons out of the nucleus? Isn't that fascinating, Anish? Just think of that for a minute. I know you just joined us, but that's fascinating. How are you getting an electron from the nucleus? Electrons aren't in the nucleus. They're found in orbits around the nucleus. They're not in the nucleus. But what the scientists have used to explain it is that they're saying that, oh, what we have at the nuclear level is we have neutrons that are then converted to a proton and an electron. And that's exactly what I wrote for you guys here. This is how we mathematically represent a neutron. It's 1, 0, n, and I'm showing that neutron being converted to a proton, which is often likened to a hydrogen atom. So that's why we have 1, 1, p, right? So that neutron is converting to 1p, and then of course our symbolic representation for an electron is 0 minus 1e. So that's fascinating how we're going from a neutron to a proton and an electron. So that's how we're able to get these electron-like particles called beta particles from a nuclear decay, a nuclear disintegration, so to speak, right? And so I show this example here where we have our carbon-14 isotope, which is largely used for carbon dating to find out the age of fossils. And I'm showing you that when that carbon-14 undergoes a radioactive decay, a beta decay, right? Because we have a we have a neutron that's transformed into a proton and an electron. Essentially what we have, what's going on with the mass number is that the mass number doesn't change, right? Because if you remember, the mass number is made up of the proton and the neutrons, right? And what's happening is the neutron is going to a proton. So you lose a neutron, you gain a proton. So that number stabilizes, it levels out, right? You're -1, you're +1, it cancels. So the mass number stays the same. But as far as the atomic number goes, you see that you're actually gaining. You're gaining. How I would say this now, you're to a certain extent you're gaining an electron. So there's a change, or you're gaining a proton. Let's say that you're gaining a proton. So that manifests itself in an increase in the atomic number. So that's how we're able to go from carbon-14 on the left to nitrogen on the right? Because the mass number of nitrogen is 14 and the atomic number is 7. So that's how we're able to get nitrogen from carbon. So if anybody ever asks you, how would you get nitrogen from carbon? How are you going to get nitrogen from carbon? It is if that carbon undergoes a beta decay. You're going to get nitrogen, and of course that symbol there that represents that release of that beta particle. So are we all clear on this? Is this clear to you guys? Give me a thumbs up so I know that we're all clear on this concept and that we all just learned something really fascinating, right? That you can have these neutrons that form protons and electrons, and as a result of that, we get nitrogen from carbon. Like, what? That's so fascinating. Am I the only one that's like really just so excited about this stuff? That's just so fascinating. That's so cool to me. Anyways, so now we're on to gamma decay. So I'm going to show you gamma decay and then we'll move on, okay? But I just want to make sure that we're all clear on this and that we're seeing this amazing stuff that's happening, right? As far as nuclear decay, decays go. Okay, so let me clear this because I need space to write the gamma one. It's not that tricky or that different than anything that we've had, but let me just do that, write that here for completeness. So we're on to gamma decay. Does anybody know what happens in gamma decay from a mass number standpoint and an atomic number standpoint? Anybody wants to share that? Anyone remembers that from class? What is a gamma particle like? What's a gamma particle like? What do we liken it to? What do we liken gamma particles to? Anybody? Any guesses? What are gamma particles like? They are like, well, they're high energy sources, high energy radiation, right? That's how we typically describe it. High energy, high electromagnetic radiation, high energy, right? And so when I said it's like a ray, that's exactly right, Beyonce. And so last time when I said this, how the penetration depth, and I was talking about how, alpha particles, let me get my sheet of paper and show you that again. Alpha particles are stopped by a sheet of paper because they don't have that much energy. Their penetration depth is not that deep. They can't go that far, right? So I have a sheet of paper and I put it here and I have a beam of alpha particles coming at it. It's gonna stop. And then beta particles, I said those would be stopped by a sheet of foil, right? I have a foil paper and I put the foil paper here, and I shoot beta particles at it, which are like electrons. They're not going to go that far. They're going to be stopped by that foil. They go further than the alpha particles, but not that much further. And the reason why they go further is wrapped up in their weight, right? And that electrons are lighter than helium nuclei, right? And helium nuclei is what we liken these alpha particles to. So alpha particle gets stopped by a sheet of paper. The beta particle gets stopped by aluminum foil, and the gamma rays, which is where we are, gamma rays are just like fast, high energy. They're just like boom, 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 right? So the penetration depth of those are much further. And so those are stopped by a thick sheet of lead, right? A lead is what would stop those gamma rays. And so similarly, when we're talking about an equation for a decay by a gamma decay, right? We're gonna show that as a electron is very light, but a high energy one, right? So that's the difference between beta and gamma is larger. That we liken it from a electron standpoint. That's how we would describe it, but it's like high energy beam, like a high energy ray is what we call it, right? So let me write an equation for that then. So typically when we talk about gamma rays being emitted, they're generally emitted like the alpha particles and the beta particles, and we call the process really where you have gamma decay, it's called an electron capture, right? It's an electron capture. So this nuclei that we have, I'm going to show you for argon, right? Argon is a noble gas. And I'm going to show you for argon, when argon undergoes electron capture in that gamma decay event is a capture of electrons. And I'll show you for argon what that looks like. So what we would have then is argon is this 3718 AR, right? And this argon is capturing an electron, and mathematically represent an electron by 0, -1, and E as I wrote last time. So guys, tell me something. If this argon is capturing this electron, right? That's how gamma decay works, right? The argon nuclei is capturing an electron. From a mass number standpoint, what's going to happen? From a mass number and an atomic number standpoint, what's going to happen? I need somebody to tell me that. It's just a mathematical thing right now, you know. We're just explaining the mathematical things with words, right? So from a mass number standpoint, what's going to happen to this element? What's going to happen from a mass number standpoint? And what's going to happen from an atomic number standpoint? I need somebody to unmute themselves and tell me. Anybody?
Miss, the mass number will remain the same, and the atomic number will be 19.
Could be what?
9. Wait. Miss 17.
Exactly. It's gonna lose 1. It's actually yeah, the atomic number decreases by 1, right? So it captures that electron, and so you end up with what is this, Beyonce, that I'm gonna end up getting? What is this? Do you see that? What is this that we're getting from argon? An electron capture or a gamma decay. What are we getting? What is that?
Chlorine. I'm not sure.
Chlorine. Can you imagine? Did you guys know that? Did you guys know that you could get chlorine from argon? From a gamma decay? You see that? Do you see how this is like?
Trouble argon because it's a noble gas. So
yeah, so you don't mess with it typically, right?
So that's really, yeah.
Yeah, it's like the isotope, right? It's a radio isotope, right? That's the one. The radioisotope argon is the one that would do that electron capture in that gamma decay to give you chlorine, 3717 Cl. That's chlorine, right? And so they're saying that a proton is converted into a neutron for this case, but I don't want to confuse you guys too much with that stuff. But essentially, that's kind of what happens here. But from an equation standpoint, that's how you would depict it, right? You have an electron capture. So think of it, always think of gamma decay as an electron capture event where whatever your isotope is, your radioisotope is gonna capture an electron. And by capturing that electron, its mass number remains the same, but the atomic number is gonna change. It's gonna decrease by 1, right? And that decrease typically gives rise to a different element. Okay, is that clear? Are you all good on this? Let me know, give me a thumbs up, and I'll keep it moving. Wow, guys, we spent a lot of time on that, but at least I hope it's very clear to you now. And I'm gonna attempt to start atomic orbital theory / electrons, so shells and subshells right now. Okay, so that's where we are now. But I hope that this was like interesting and helpful to you guys to see what these equations for radioactive decay look like, because you can definitely, there's a high probability of it's coming on an exam. Even if it doesn't come on the paper too, it will definitely can show up as a multiple choice, right? And in the event that it does, you would be well versed in this idea as to what happens from a nuclear standpoint and a mass number and atomic number standpoint, okay? So I'm gonna clear this. I'm gonna advance to the next slide. We only have 9 minutes. I'll see how far we can get as far as subshells and all this stuff goes, but that's where we are now, okay? So I'm gonna advance the slide to that, and we'll talk a little bit about that. Ivanita, I see you. I see your question. Okay, just give me a minute here and I'll see if I can take a look at it. But give me a minute here. Let me just wrap this stuff up now. You're Benita, what unit are you again? You're unit 2, right? Yeah, okay. Just give me a minute. Let me wrap up unit 1 and then I'll see where we are, okay? Okay, so we have roughly 8 minutes, right? And so really, I'm just gonna be able to get into some definitions for you for these, give you some definitions for like, this whole idea of energy levels and emission spectra. Like just now we were talking about electrons and where we find electrons, and that we were taught that electrons are found in orbits, like they're rotating around the nucleus. They're not in the nucleus. They're in what we call these shells or these energy levels, right? So that's where we would typically find electrons, right? And so this is a level up from CXC from the standpoint of now we're actually giving them numbers and we're giving them letters. We have what we call subshells, we have molecular orbitals, atomic orbitals, all these different things which didn't exist in CXC, right? And so the idea, I guess like the foundational principle is that you have this, they call this branch of chemistry, really, if you're supposed to delve deeper into it, it's like quantum chemistry, right? And so a quantum, we typically talk about a quantum of energy, and that's like the fixed amount of energy that it takes for a change to happen in an electron, right? So for it to go from one level to another, there's a quantum of energy that is required for that change to take place, a fixed amount of energy, and we call that the quantum of energy, right? And it's like really like a foundational thing, like a quantum of energy is a fixed amount of energy that is required for a change to occur in an electron, right? So we have these electrons in these shells or these orbits or orbiting the nucleus, and it takes a quantum of energy for any change to happen in that electron, right? And so our next definition is this idea of the energy being quantized. And if the energy is quantized, we mean that the energy is fixed. Just as we said, the quantum is a fixed amount of energy, but it's quantized, meaning it's fixed. It's a fixed energy. And if another way of saying that energy is fixed is saying that the energy is quantized. The energy of electrons are quantized, right? So it's quantized, it's fixed. Like you have to have that amount of energy for anything to happen in an electron. Otherwise, it's just gonna sit there. It's not gonna move. It's not gonna get kicked off and again ionized, right? As we will eventually talk about an ionization, energy is a fixed amount of energy that you need for that electron to move into another energy level or to do anything. You need that a quantum of energy, and so we say that the energy is quantized. Okay, so then now we can talk about a ground state and an excited state, right? A ground state is that basic level that the electron is in. It's content, it's happy, it's stable, it's in a ground state, right? That's the lowest energy level that's possible. And that's when the atom is most stable. It's when it's in its ground state. So you'll often hear about a ground state. Ground state is just a ground, the basic level, we're happy, we're stable. Then we have an excited state. If you give it energy, the electron is in the ground state and you give it energy, it gets excited. It goes into an excited state. But the excited state is not stable. It's often short-lived, right? It's excited, but then it will want to go back to the ground state because it's not stable. It wants to go back where it's stable. We're excited for a little bit, but then we have to go back to the ground state. So that's kind of how it works. But to get to that excited state, it needs to overcome that quantum of energy, get that quantum, and then it will be able to get to move from one level to another. Okay. So I'm just gonna do a quick sketch to show you what that looks like from an atomic structure standpoint. And then I think we'll have to wrap up there in the interest of time and then pick up next time, okay? So let me show you a ground state. So the ground state would be, all right, you have your nucleus, and then you have your first shell, right? So that's this N=1 shell. And so you have your electrons there. So you have one here and one here, right? And then you have your another shell around it here, right? So we just now I draw a nucleus or N=1, and I'm drawing these other energy levels that would be your N=2 and your N=3 around it. So that's what I'm drawing now. And this is our ground state, right? So the ground state, closest to the nucleus, stable, right? Ground state, this is a stable state, right? But we want to go to an excited state. For whatever reason, if you give it energy, it's gonna go to a higher level. It's gonna level up. It's gonna go to a level up from the nucleus there. It's in N=1 here, it's close to the nucleus. If we give it the energy, we're gonna, and we give it that quantum of energy, it's gonna be then promoted, or it's able to then be promoted to a new energy level. That N=2, wherever the energy that you give it allows it to go, it's gonna go. So what that might look like then, guys, is that electron being able to move to another level. So how would I say, instead of me, should I draw the whole thing, or can I just show you guys an arrow? I think I want to draw it for completeness. So let me just draw that real quick and then we'll wrap up there. So we have our ground state and we have our excited state, right? We give it the energy that it needs, a quantum of energy. It's going to be able to do the work that it needs to do to move to the next level. So let me just draw that real quick. First of all, let me get back my mouse. I think that's the best way to go forward with these things. Ooh. I think that's the best approach here, is to get back my mouse and then go from there whenever it freezes like this. Okay. Okay, so let's finish this sketch. And let me just show you the excited state. So, okay, we still have our nucleus, right? We have our N=1. That's that first level, right? Then we have our second level. And of course, that's a circle, guys. Don't let this hand-drawn thing fool you. It's a circle. We're talking about spheres, right? That's how we represent the shells, right? All right. So previously we were here. We gave this atom energy. So essentially we're giving that electron energy. It's getting excited, right? It's excited now. And so, all right. It's getting excited now. My pointer keeps on just vanishing and I don't know why it does that. So that's why I'm like always like a little bit delayed with this drawing thing. But let me show you. Can anybody make any guesses as to what's gonna happen? Or how is this figure gonna be completed now? We have the electrons in the ground state on the left, and then we give it energy now. So we were able to give it that quantum of energy that it needs. And so essentially then we're gonna have that electron being promoted, right? To this just let me show you 1, 2. So it's in the second one now, right? Before it was like here, it's in the second one. So it's out here in this second ring. So now it was in n equal 1, now we're in n equal 2. Right? So because of that quantum of energy that we gave it, it was able to level up. Right? Everybody knows what leveling up means. Oh no. It's able to go to a new level because we gave it that energy, that quantum of energy that it so desired. So it's gonna go from, oh Lord. It's gonna be here. Don't mind that blob of stuff, it's here, right? And that as a result of that energy that we gave it, it got promoted to a new level. Okay, so that's kind of how these energy quanta works. That's how this leveling up works. That's how you go from a ground state to an excited state. Right, do you guys see that? Is that clear? The two blobs that I just drew? Okay, all right. So we're gonna wrap up there for today. We didn't cover a lot, but what we did cover was some interesting and fundamental and foundational stuff. So I hope that this was useful for you guys, and we'll continue. We'll pick up next week, okay? How is that for you guys? We're gonna switch on over to Unit 2 now. So I have a question from Venita. So I'm going to pull up Venita's question and see what we can do there. But you're very welcome, Chanel. I hope that was helpful to some extent for you. Beyonce says, thank you. You're welcome, Beyonce. Let me stop sharing this real quick so I can see if I can get Venita's question. You're most welcome, Beyonce. You're welcome, Anish. Have a great rest of your Sunday and have a great week. And look on the Instagram page this week for a question. I'm going to have a question for CAPE students this week. I've been giving the CXE students all the love and giving them chances to win. I'm going to give the CAPE students a chance this week. Okay, so definitely look on the Instagram page. Make sure you're following us on Instagram and you get a chance to win one-on-one. I'm giving away one-on-one session.
What's the name of the Instagram?
I'm putting it in the chat now, okay?
What's the name of the Instagram?
So it's LMD and STEM Academy. I just put it in the chat. You see it? Oh no, I didn't send it to Venita. Let me put it to everyone.
No.
And then you just follow us, and then I'm gonna post quiz tomorrow. I'm gonna post one for CXC and one for CAPE. Or maybe I just do CAPE because I've been giving away all the things to the CXC students. And the CAPE students haven't been getting any love. So I might not give them any quiz this week. So that's it, right? Did you see it? Anish?
Yes, yes.
Okay, all right then. So look out for our quiz tomorrow, okay? And definitely answer, participate for a chance to win a free one-on-one session. All right, so all right, guys. We're gonna start Unit 2 now. So who is here for Unit 2? If you're here for Unit 2, raise your hand for me. Raise your hand so I see that you're here for Unit 2. Okay, so Venita is here for unit 2. Let me see. Where's my thing with your question? Give me a minute, okay? Give me a minute real quick. Okay, so I'm looking at it now. I'm looking at the question now. Venita. So I see that Abisola came back. Welcome back, Abisola. I see you're a woman of your word. You came back. Okay. Who is this? Oh, somebody, give me a minute. Somebody said that they signed up and then. I'm figuring out how I can get your question on this screen. So let me see. Kayla was given 3 different alcohols, each with molecular formula C4H10O. She observed that only 2 out of the 3 alcohols resulted in a color change from orange to green when warmed with acidified dichromate. So propose an hypothesis for her observation and design an experiment to test your hypotheses. Is that the question, Venita? You can unmute and talk to me, no, Venita. Unmute and talk to me. I'm gonna see if I can share it on the screen so we're all seeing the same thing. Welcome, Duran. I just saw your message. Hopefully you're unit 2 and that you didn't just completely miss unit 1. What unit are you, Duran?
Unit 1.
Oh no. Okay. So this is streaming live on YouTube now. So it's probably gonna be streaming. Actually, I don't know if you can go back to the unit 1 stuff. So this is streaming live on YouTube now, and this is like when it ends, you're gonna be able to watch everything, and you just like start from the beginning and watch the unit 1 stuff. And then you can ignore this part of it. But I'm not sure. Like if you go to YouTube now, go to YouTube and try it and let me know if you're able.
But over that, like I don't know a YouTube channel.
Okay,
is there like a WhatsApp group as well?
No, we don't have a WhatsApp group. I'm gonna give you the link to the YouTube channel, and then you can see what you can find there. And even if you're not able to watch back what we just did today right now, you'll be able to watch what we did for the last week, okay? For unit 1. So I'm gonna give you the link to the YouTube channel now, and then you can go over there and see what you missed. And then once this is finished streaming, you'll be able to watch what we did today, okay?
Yes, miss. So miss, wait, one more question. What time is unit 1?
Or
What
unit
time?
one is from 4:30 to 5:30. So you literally just missed it. Do you follow us on Instagram? Because I have
No, we're gonna friend send me the link.
Okay. Okay, I'm gonna send the links. I'm gonna send you a link to the YouTube channel right now. And then definitely follow us on Instagram because I have the times for the classes there. So you literally just missed unit one. And we had a very good session today. Well, you can watch it on
What
the
did we talk
YouTube. I'm
about,
gonna
miss? And you
We did atomic structure. So we're talking about we were talking about radioactive decay. And then we started energy level. So like ground state, excited state stuff. Have you learned that already?
oh no, miss, because we're out of time, like you cannot jump over some of the things I teach.
Okay. Yeah, I find that that's happening a lot, that people are kind of like, it's all over the place, right? Which is kind of tough, that you're not learning the things in order and you're not learning everything, right? It's kind of tough, but that's Corona. It's Corona time for you. We just have to make the most of it, okay? And that's kind of why I'm doing this free session. And I'm doing it I can't cover everything, but I'm covering what I found to be the most fundamental things in a methodical way that you'll at least have the ground state, the fundamental stuff, okay?
Yes, miss.
Okay, so look in the chat now and you'll see the link to our YouTube channel and you'll see the link to our Instagram page. I have a lot of giveaways on the Instagram page. I give away free session, free one-on-one sessions. So definitely watch there, follow us there. Do our quizzes and enter for a chance to win, okay?
Yeah, but that no miss, like easily distracted with social media, so I cannot delete Instagram.
Oh, okay. Well, stay on YouTube then and talk to me in the comments or email me or whatever the case may be, okay?
All right. Thanks.
Okay. Okay, you're welcome. Okay, so I'm pulling up Benita's question now. For you, Unit 2 guys, an organic chemistry question. She's asking me, oh, let me download it actually. Let me download this image. So I have the image on my screen and then we close
Miss,
this.
one last question, miss. What is your name, miss?
Nyla.
Oh, nine. Oh, miss,
Nyla.
what school do you teach, miss? If you don't mind me asking.
I teach at my own school, LMD and STEM Academy. That's where I am. Yeah. Which school do you attend?
Excelsior, miss, high school.
Okay. Yeah, no, I don't teach at a school that exists. Well, let me not say a school that exists. Like I'm starting this STEM Academy, right? That's largely focused on just the STEM subjects. I want it to be that specific because we need academies of this sort that really specialize in science, I find. And so I'm keeping it at that level. Very niche, right? Very niche. It's only science stuff. I mean, it will expand eventually to include other things that I think are tangential and foundational and fundamental or things that go hand in hand with STEM. Like I'll develop courses around those, but right now it's just like the fundamental basics, bio, physics, chemistry, math. But right now we're only doing chemistry. I will eventually expand to include those other subjects and then add those courses as well. But right now it's just chemistry, okay?
Yes, miss. If you want me to take school shot at chemistry teacher, they can come.
Excelsior. You don't have any chemistry teacher down there?
Yeah, I have one of them shot at teacher.
Okay.
My extra teacher.
Okay. I'll consider it. Thank you for telling me that, okay?
Yes, miss. 137 Mountain View Avenue.
Okay. Thanks for letting me know. But in the meantime, Duran, you can direct your friend to us over here and let them know that we're doing free chemistry classes
Yes,
for
miss.
the rest of February. What was that?
I sent out the link, miss.
Okay, yeah, and let them know. Those who are on social media can follow us on Instagram too, and they can win prizes. Tell them, okay?
Yeah.
Okay. All right. Thank you so much.
All right.
All right. Let me open this now, Benita. Sorry. Sorry about that. I'm gonna open it now, okay? So this is a question. Can you guys see it? Whoa. Did you guys see that just now? Okay, let me. Oh, let me share it again. Okay, I'm gonna share it again so you can see the question and then we can think about and talk about it a little bit. Okay, so this is the question. Let me know how that is showing up for you. Do you see anything in the background, or is it just the thing that you're seeing? Okay, just the question. All right. So let's see if we can think about this a little bit. Let's see if we can think about this a little bit. Abisola, are you seeing this?
I'm seeing it.
Okay. So we're given, and I want you guys to talk this through with me, right? It's really pulling on your knowledge of a lot of different things, right? It's pulling on your knowledge of oxidation, reduction. Well, I'm giving away the answer. We weren't quite there as yet. But Kayla was given 3 different alcohols. So you have 3 different alcohols. They're the molecular formula C4H10O, right? So what might that be? Because they have the same molecular formula. So right away, what are they? They're all alcohols. So they all have the same functional group. But they're different in there. Like, what could be different about these alcohols? Think about that with me, because they have the same formula, right? But they're giving different different color changes with dichromates. So something is different about them that's causing them to behave the way they're behaving. And we, in week 1, I think we covered this idea of isomers and how we have structural isomers and positional isomers, where the position of the functional group might be different, right? They have the same formula. They're the same molecular formula, but the position of the functional group might be different. The structure is a bit different. Maybe it's branched in one case. There's some branching that's there. There are things that are different about them, right? And so Venita and Abisola, what might be going on here? What might be going on here? Let me just talk to me and let me know. This is a very close-knit group, tight group. So let me know, talk with me and let me know what you think might be at play here and what are we testing for and what's going on. And it's really pulling on your knowledge, right? Your understanding of all things chemistry, really, right? So talk to me, guys. Talk to me and let me know what might be going on here.
Is it that it is an isomer from the molecular formula?
Exactly, it's an isomer. So do you have any ideas how we might start drawing? Let me see if I can share a whiteboard and we can work on this and see where we end up with it. I'll probably have to stop sharing it. Let me think about it. Maybe I can write it on the whiteboard. Okay, I'm gonna do that. Let me do that. New share? Can I do a new share at the same time? Let's see. Ah, okay. What are you guys seeing now? Are you seeing just the whiteboard or the whiteboard and the question?
Just the whiteboard.
Just the whiteboard. Oh Lord. All right, I'm gonna close the question. And I'm gonna write out what I think are the key points on the whiteboard, and then we just work on the whiteboard. What do you guys think about that? Okay, so let's see now. All right, so okay, let me pull it up here. So guys, just be thinking about what might be going on from an isomer standpoint, right? Benita, definitely it's your question, so I'm gonna want you to talk to me, you know. Unmute and talk to me and let me know where you are. So I'm not gonna just give you the answer, we're gonna arrive at it together, okay? So unmute yourself and talk to me and let me know what you're thinking, where you are as far as this question goes, and kind of so I can see what you've done so far, you know, in terms of thinking about it. So it's C4H10O. So guys, what is C4? C4 is what would be that homologous series of alcohols? The mic in the device is giving trouble. Okay, so Venita's saying that she can't speak. All right. So type in the chat then. What is C4? C4 is what homologous series would that, well, the homologous series would be alcohols, right? That's the, yeah, so homologous series of alcohols with increasing carbon chain. But what I'm asking is what is this, the prefix that we use for C4 compounds? If it's 4 carbons, how do we refer to those? Abisola, do you know? Like for C4, what do we refer to those compounds that have 4 carbons as?
I'm not sure.
You remember bute, so you have meth, eth, prop, bute, pent, right? Hex, hep, remember those things? So like it would be like this, bute, right? So this, so what we're having here is this is the molecular formula, and they're saying that there are like 3 isomers of it, right? 3 different alcohols, right? But they all have the same molecular formula. So like it's like it would be a variation or varieties of butanol, right? There are varieties or different isomers of butanol, which has 4 carbons, right? 10 hydrogens and 1 oxygen, right? So we can start to draw structures for butanol. So Venita says butane, but it's actually butanol. It's the prefix that we're concerned about, and you got that right? It's butanol. That butanol because it's alcohol, right? That's the we're in the alcohol homologous series, right? So it's butanol. But there are 3 different alcohols with 4 carbon each. So they're like isomers, and you can have positional isomers, where the position of the OH is changing. So it's on different carbons each time. Or you can have branching happening. So you have branch chains, and those will affect the reactions or the character of the alcohol. So, you know, remember, I don't know if you guys learned this, but you have primary alcohols, secondary alcohols, tertiary alcohols, and that's just based on the arrangement of, I guess, the carbon backbone can be shifting as well, right? But it's still 4 carbons, but the backbone is shifting, the positional, yeah, we can have positional isomers, so the OH is in a different position, but the formula is still the same. Right, are we all clear on that? I see that Jules just joined us. Jules, welcome. Are you unit 1 or unit 2? Jules? Are you guys following so far? I don't hear anything or see anything in the chat. Are you following what I'm saying here? I want it to be interactive because like I don't want to give you the answer, just give you the answer. Like I want us to think it through so that if you're given this in an exam, you'll be able to like go through a similar approach to solving it, right? So okay, so it's 3 different alcohols. Let me write the rest of it now. Only 2 out of the 3 guys resulted in a color change when you from orange to green, when you add acidified potassium dichromate, right? So I'm gonna write that down. 1 of 2 color change, orange to green, right? Orange to green. With acidified, let me just go do a shorthand. Acidified potassium dichromate, right? And guys, what is potassium dichromate? What is this? What is this that they're testing it with? What is this? What does a test with potassium dichromate tell us? Because guys, this is the key to this question, right? We have to know what this is doing and what this color change represents. And that the fact that only only 2 out of the 3, on the fact that only 2 out of the 3 of them gave us that color change, it says a lot about the structure of the alcohol, right? So yeah, please talk to me. Jules, you're awfully quiet. To test for sulfur dioxide. Well, I guess you can use it for that, Benita, but more broadly, with acidified potassium dichromate, like I think it tests for like the oxidizing power or oxidizing ability. You have an oxidation reduction event that goes on. And from that, we can glean whether or not what we have, right, is oxidizable or reducible, right? So it's like a redox kind of a situation going on whenever we're using potassium dichromate, right? Because you have a reduction of I think you generally have a reduction of that dichromate ion, and that's what results in that color change that we see from orange to green, right? So you'll have alcohols that can cause that effect and alcohols that can't, and that's based on the structure of the alcohol. Is that clear so far? Are you following? Let me know if you're following that so far, right? So that's V1. So that's 6. So that's the oxidation state is 6. For this, I'm just putting it here because it's a reason why they're telling you what the oxidation state of the potassium dichromate is, right? The oxidation number is important because it's like based on this redox principle, right? So Venita is saying this is when the alcohol is oxidized. Is that true, Venita? Let me know. Is that true? When the alcohol is oxidized, what happens as a result of the oxidation of alcohols? When you oxidize an alcohol, what happens? The potassium dichromate will act as an oxidizing agent. An oxidizing agent oxidizes things while it itself is reduced, right? So as a result of that reduction that takes place of that acidified dichromate ion, we see that color change from orange to green, right? So the dichromate, potassium dichromate, is an oxidizing agent. It's going to oxidize the alcohol. It can oxidize 2 of the 3. 1 is not oxidizable, and that should give you a hint as to what the structure might be. But 2 of them are oxidizable, by potassium dichromate. And so that's why when you add that, the potassium dichromate itself, it oxidizes the alcohol, but it itself gets reduced, and it being reduced is manifested in a color change from orange to green. So are we all clear on that? Are we all good up to that point as to why the color is changing and why it's not?
Yes, ma'am.
Okay. All right. So what now? The part where we're at is figuring out what's actually going on from a structural standpoint. 2 of the 3 can reduce dichromate or can be oxidized by dichromate. 2 of the 3. So what does that tell us about the structure of 2 of the 3? That's where we are. And I want you guys to answer. Or is it, have you guys learned about this or no? Or am I teaching you this right now? Do you have any ideas or no? Because I'm assuming that you were taught it, Benita, which is why they're asking you. I'm assuming that you have some basal level of knowledge on it. Otherwise, they wouldn't be testing you on it. Is that correct, Benita? Or are they expecting you to go and research this stuff and figure it out on your own? Okay. Okay, I see. All right. So, okay. So I haven't taught you guys extensively about all the different functional groups, but you see alcohols. Okay, so as I said, the potassium dichromate is an oxidizing agent, right? So it can oxidize things. And by oxidizing things, I mean that it can cause things to, so we can define oxidation in a variety of ways, right? Oxidation can be when a compound gains an oxygen, right? It can be when a compound loses hydrogen, right? It can be when a compound loses hydrogen, that's oxidation too. It can be a loss of electrons, right? Because oil rig, right? It can be a loss of electrons. And it can also mean that there's an overall reduction in the oxidation state or the oxidation number. So those are just definitions for oxidation from an oxidation standpoint. So when I say that potassium dichromate is an oxidizing agent, it can either cause that change to happen in another compound. The compounds of interest here being the alcohols, right? So the potassium dichromate can cause the alcohol to gain oxygen, lose hydrogen, lose an electron, cause an increase in the oxidation number or the oxidation state. So those are the things that the potassium dichromate as an oxidizing agent is capable of doing. While it itself, the potassium dichromate is reduced in the process, and that reduction results in that orange to green color. Okay. So where we are now is then, we have 3 main classes of alcohols, right? In terms of from a structural standpoint, right? We have primary alcohols, right? So we have primary alcohols. We would generally write them as, you can write 1, I guess it's kind of like first degree alcohol, is a primary alcohol. You have secondary alcohol, right? Secondary, I'm not gonna write out the entire thing. And then we also have tertiary alcohols, right? Now, a primary alcohol, I have to show you the structure, otherwise it's not gonna make sense. But are you guys familiar with this concept of primary versus secondary versus tertiary, or is this news to you guys right now? Let me know in the chat or just unmute and let me know if you're comfortable, if you're familiar with this concept of primary, secondary, and tertiary alcohol. Let's see what you guys are saying. Not too familiar. Okay, so for primary alcohols, what can I erase off of this? What can I erase? Oh, maybe I'll write in this corner. I haven't written over here as it. Let me write over here. So primary alcohols, the OH group, because okay, remember that alcohols, the functional group is OH, right? The functional group is this OH. Right? For alcohols, that's our functional group. Functional. Right? That's our functional group. Let me circle that in a red thing. Do I still have my pen? Okay, so this is our functional group, right? This is the functional group. This is the thing that makes it an alcohol. Like this is it for alcohols. The OH group is what gives its character, its chemical properties, the kinds of reaction that is then able to partake in is as a result of this functional group. That's that OH group, right? All right. So the position of that OH group is kind of what determines whether it's primary, secondary, or tertiary, right? So for a primary alcohol, the OH group is at the end or the last part of the chain. So OH, let me write that. 1 degree, so that's primary. OH at end or last part of chain, right? And then the secondary one, the OH is in the middle of the chain, right? And the OH is a functional group in OH in middle of the chain, right? So that's that for secondary and tertiary now. For tertiary, it's the OH is like a branch point. So like where you have like branching is where you'd have this OH group. I want to draw it. I would rather drawing this to show you guys, but I think that we can just do that. I can just tell you that, guys, tell you that for now, and you later look a little bit deeper into it. But I want to like talk about what's happening from an oxidation standpoint and a reduction standpoint, and why two of them have color change and why the other one doesn't have a color change, right? And that's something that's largely based on the structure. And as I just went through primary, secondary, tertiary, like that's why some of them change and some of them don't, right? So the question is asking you, Benita, to propose a hypothesis for her observation and design an experiment to test your hypothesis. So Benita, what would be the hypothesis here based on what I've said so far? Right? Without me going any further and giving you the answer. The hypothesis is just an educated guess as to what might be going on here. Right? So what would be your educated guess? I mean, I've already told you the answer, I think, in terms of what's going on, but I want to see if you're grasping it and if you're picking it up. So you can write in the chat because you say your mic is giving problem. And then also, Abisola, definitely feel free to talk with me and let me know what you think is going on here. So what's your educated guess? What's the hypothesis? I've essentially told you guys, but I want to see how much of that you are grasping, okay? So Venita, write that in the chat. Abisola, unmute yourself and let me know where your thoughts are with this, okay? Yeah. Any thoughts? Any thoughts? Any thinking? Anything going on there? Okay, Avenita, I hear you. Abisola?
Miss, I'm trying to put one together.
Put one together. You putting a thought together? So I'm giving Venita a minute. I'm giving you a minute, Abisola. So let me know what you're thinking. I didn't give you all the answer, but I gave you enough for you to be able to kind of deduce what's going on. Okay? All righty. Where are we? Okay. So Abisola is saying that she's not too sure. So essentially, maybe I'll do this. I don't have the space there and I don't want to erase this stuff because I think it's all important. But essentially, I just taught you guys about primary alcohols, secondary alcohols, and tertiary alcohol, right? Now, in terms of where the functional group is, the OH group is, like that's what determines whether it's primary, secondary, or tertiary, right? Primary alcohols are oxidizable because the OH group is at the end, so you have more leverage, right? And I guess in terms of how would I say? Its ability to be oxidized, more oxidizable. It's a more oxidizable hydrogen, right? It's a removal of hydrogen. It's a more oxidizable hydrogen because remember we had a definition for oxidation as the removal of hydrogen. So that hydrogen, because it's more exposed, it's more removable in the primary alcohol case. And so primary alcohols can be oxidized to aldehydes, and then after that you can get acids out of it, carboxylic acids, right? So in light of what I just said, potassium dichromate is a powerful oxidizing agent, so it oxidizes something else. So the potassium dichromate can oxidize the primary alcohols to form either an aldehyde and then after that acid, a carboxylic acid, right? Secondary alcohols are the same. They're oxidizable, right? And so the potassium dichromate can oxidize that secondary alcohol, and what you would get from the oxidization of a secondary alcohol is what we call a ketone. That's a different functional group, right? So those two of the three are oxidizable, right? And so they are indeed oxidized when we expose them to acidified potassium dichromate. So that's kind of the answer, Venita. So the hypothesis could then be something as you could say, two of the three alcohols are oxidizable. So I hypothesize then that we have a primary and a secondary alcohol and also a tertiary. But the tertiary cannot be oxidized. The tertiary is not oxidizable. And so when you react to that particular one with potassium dichromate, you don't see a color change because it's not oxidized, right? The alcohol is not oxidized by the dichromate, and the dichromate by extension is not reduced as a result of that interaction. And so there's no color change that you see from a dichromate standpoint, right? So the primary and the secondary alcohols are oxidizable, right? And they are oxidized and you see a color change, but the tertiary one is not oxidizable and it's not oxidized, so you don't see a color change, right? So your hypothesis is that, well, it looks like we have a primary and a secondary and a tertiary. Primary and secondary undergo oxidation, and that's why we see that color change. The tertiary does not. How can I test this? How can I test this? Well, you do that, you probably would need to do another kind of a test. You're given your results as to what happens with the dichromate. So maybe you could use another oxidizing agent that whenever that is successful in oxidizing a compound, there's a color change that accompanies that, and you can see that for yourself, and then you can just confirm what you're seeing with the dichromate. Does that make sense? I hope that makes sense for you guys. But if not, I'm happy to explain again. But does that make sense to you guys? Just let me know. Indicate and let me know. Abisola, you can speak, so definitely speak. Unmute and talk to me. Venita, please write in the chat what's going on.
You can go over it one more time.
Okay, so what I'm saying is that you have these, so within the family of alcohols, there are levels to this, right? There are levels to this. You have a primary alcohol, you have secondary alcohols, and you have tertiary alcohols, and that's structure dependent, right? Now, the hydrogen from that OH group, right? Because the OH is a functional group for alcohols that I showed you here. I wrote it here and I boxed it in red. This hydrogen is more oxidizable, and by that I mean you can take it off, right? When it's in a primary alcohol state or a secondary alcohol state, right? Tertiary, not so much. Tertiary, you're kind of stuck with that, right? So what happens is if you expose it to an oxidizing agent like potassium dichromate, right? The potassium dichromate is gonna oxidize it, and you're gonna remove that hydrogen, right? You're gonna change that oxidation, so you're gonna oxidize that alcohol. And that oxidation, you can measure, you can track based on the color change that happens as a result of the dichromate being reduced. Oxidizing agents oxidize other compounds while they themselves get reduced, right? And because the dichromate is reduced whenever it oxidizes the primary and the secondary alcohol, you see that color change from orange to green. For the tertiary alcohol, because it's not oxidizable, when you add dichromate to the tertiary alcohol, you're not going to see any color change because it's not oxidized, and because it's not oxidized, the dichromate is not reduced, and so you don't see a color change from orange to green. It just stays the same, right? And that's because of the structure of these alcohols that are in question. We have the same molecular formula of C4H10O, but the difference is in the structure. They're structural isomers of each other. And in that structure, you have a primary structure, a secondary structure, and a tertiary structure. Primary and secondary structures are oxidizable, tertiary structures are not. And you can test that using a powerful oxidizing agent like potassium dichromate or another one of your choice to just kind of confirm that what you're seeing with the dichromate is actually correct. So my homework for you would then be to go and research another powerful oxidizing agent. What's the accompanying color change? And then you can say, oh, I'm going to test it with this. And if it's primary, this is going to happen. If it's secondary, this is going to happen. If it's tertiary, this is going to happen. And convince yourself that, oh, it's as a result of the oxidizing ability of these alcohols. Does that make sense?
It does.
Well, what did you say, Abisola?
I was saying it makes sense.
Okay, so that's kind of what that's what the basis of this is. It's understanding that different structures give you different things. Different structures can do different things, and you have these class of compounds that are either oxidizing agents or reducing agents that can tell you what's going on because they can oxidize or reduce or whatever the case may be. They're able to do that, and there's a color change that accompanies that. And from that, you will be able to say what's going on there, okay? So Benita says that's understood. I hope that was helpful. And I'm always like leery of like helping students with these things because I don't want to give away the answer or give you spoon feed it to you, but I want you to think about it critically, right? And so when you're faced with a similar problem, you know how to think about it and think it through and work it through for yourself. Okay? Okay. So this was like a very practical session today where you're actually seeing a question with alcohols in practice when you have to think about isomerism from a structural standpoint, right? You have to think about what the different structures are capable of from a primary, secondary, tertiary standpoint. And then you have to couple that with this idea of oxidizing agents versus reducing agents, what's oxidizable and what's not, right? And so you start to put all these pieces together, and then you'll find that your understanding of organic chemistry will grow and grow and grow. Okay? So Benita says, thanks a lot, Miss. I have a way better understanding now. I'm very happy to hear that. That's why I do what I do, is so that you understand and you really have a good grasp of it, right? So you can then build on that. Okay? So Abisola, that's clear for you as well, you said?
Yes, Miss.
Alrighty. So I don't want to dive into any new content today. I think that was a solid lesson in and of itself for you guys today. So I am open to taking any questions that you might have, not necessarily a question to solve per se, but like questions about anything that you might have about what we're doing here with these classes, where you can get more information. Of course, you know, this is being streamed live on YouTube, and I have it's already in the chat, the YouTube link, so you can go back and watch it. You can follow us on Instagram so you can see any giveaways or any updates. But if there are any questions from your end, definitely let me know that. Now we have about 8 minutes, and I won't start anything new. So just let me know. Just ask me your questions while I'm here now, and then we can wrap up for today. So Abisola, which school are you at again?
Brownstone Community College.
Brownstone. Okay, and Venita, where are you joining us from? I'll see what she puts in the chat because she says her mic isn't working. So she says she's joining us from Trinidad, Waterloo Secondary. Okay, welcome. Welcome from Trinidad. So you're in upper 6, Venita? I'm guessing you're in upper 6, right? Unit 2, and then Abisola is in Unit 2 as well. From Brownstown. Okay, all right. So then how is your understanding of the other concepts, both of you? How are your understanding of the other concepts that you've been taught so far in upper 6? I'm guessing you've done spectroscopy, NMR, all this other cool stuff. Where are you guys with that stuff? How is your understanding of that?
I can understand those stuff now because I had, like, for module 1, we had a teacher who she really did teach chemistry. So it was kind of rough on us on that part until January. Our teacher who was supposed to teach, who teaches in Unit 1, came back and she had to go over those stuff, and so kind of understood it much better than how the other teacher teach the module 1. But like for other stuff coming forward, understand those stuff now.
Okay. All right, that's good. So you have a good grasp of the spectroscopy stuff in general, then you would say. Oh, well, a fairly good grasp.
Yes.
Okay, and then how did you say organic chemistry is going for you so far? This stuff that we just did?
Yes, I'm kind of still like trying, like basically that the naming molecules part, miss.
Yeah.
I have little complications with those at times.
Yeah. It can be tricky. It can be tricky to figure out that. With the IUPAC naming, right?
Yes.
Yeah, it can be tricky. But don't get too hung up on that. I mean, it's important because as you see here, this would be kind of a naming problem or a branching and drawing stuff differently, right? That's what this problem was based on. So it's important, but there are also more things that you need to focus on and not worry too much about naming. Does that make sense?
Yes, miss.
Like there are more complicated concepts, I think, in organic chemistry than naming. So don't worry about the naming too much. Definitely grasp it, spend the time to understand it, but don't worry about it too much, okay?
Yes, ma'am.
Okay, and then Venita, how are you doing now? You have any more questions or how is everything now? Like I know you said that's a lot clearer, but if is there anything else that you want to ask me or talk about right now? I'm gonna clear this screen, okay? Were you guys taking notes or were you just like listening? How do you approach this? Do you take notes or do you just like or do you I said Deandra, were you there all along? I literally just saw you. Okay, Venita, she took a screenshot of everything. Alisola, were you writing? Did you take notes like that? Like write it down, or how do you process this information?
I wrote down little jottings and stuff.
Okay, great. All right, Deandra, talk to me, Deandra. I saw that you just, okay, I just got this link. Okay, okay. What unit are you, Deandra? Are you unit 2 or unit 1? Unit 1?
Yes.
Okay, so you can definitely join us next week at 4:30. I do unit 1 at 4:30. So this is unit 2 that we're just wrapping up now. So join us next week at 4:30 for unit 1. And then in the meantime, you can oh wow, what did I just do? In the meantime, you can follow, let me drop the link for the YouTube channel there. I hope I didn't mess up the stream. I'm gonna drop the YouTube channel here. So that's our YouTube channel. Can you see that, Deandra? So you can go there and watch what you missed today and last week from a unit 1 standpoint. And then follow us on IG so you'll be updated on what's going on. And I have giveaways there. I have quiz questions that you can play and win prizes. The prize right now largely being a free one-on-one session with me. So we can talk about your questions, your chemistry questions in particular. So you can play for a chance to win. Okay, so answer the quiz question and play for a chance to win. So yeah, so that's kind of where we're at. So thank you for joining us. And definitely subscribe and watch our YouTube so you can see what we've done so far as unit 1 go. Where are you in your class on unit 1? What topic are you at?
We're at module 2. That's what rate of reactions.
Rates of reaction. Okay. So how comfortable are you with atomic structure stuff? Because that's what I was covering. That's what I've been covering for the month of February. Atomic structure, so like atomic orbitals, subshells, SPD, and energy levels, and emission spectra, and all that stuff, and radioactive decay. How comfortable are you with that stuff?
I'm having a few issues that, especially with SPDF notation, I'm having issues with that.
Yeah, okay. We didn't quite start. I mean, I just grazed the surface today. I'm talking about energy levels and ground state, excited state. That's what I touched on today for unit 1. So we're gonna build on it. I guess we have 1 more week left really of these free classes, and that's next week. So hopefully I can get that stuff done next week. And then we'll see where life takes us after that as far as these chemistry classes go. But you're here now, so definitely subscribe to our YouTube channel and see what we've done so far. And follow us on Instagram and feel free to DM me with any questions that you have, okay?
Okay, thank you.
And definitely tell your friends. I'm taking it that you're from Excelsior. Are you from Excelsior?
No, I'm from Malta Vernia High in Montego
Okay.
Bay.
Okay, all right. Okay, so definitely share with all your classmates and your friends and let them know as well that they can come and find resources here that can help them for their exams, okay?
Okay, will do.
All right, have a great week then. And Abisol and Venita, I think that we're all good too. I don't think you guys have any more questions from me based on what I see in the chat. So it's exactly 6:30. So we did excellently with time. And so I'm gonna go ahead and end our meeting. As I said, this is online, it's being live streamed on YouTube now. So you'll be able to see it there, okay? I see that Tisha Thorpe just joined us. Tisha, welcome. We're wrapping up now. But I can give you what you need to stay connected with us and watch what we've done so far. So Tisha, welcome. Where are you
Thanks,
from?
Miss.
Where are you from and what unit are you?
Unit 1, Miss. I attend Mount Alvernia High School.
Okay, all right. So you know Deandra then. You probably know Deandra?
Yes, Miss.
Okay, so I'm gonna do this again because you just joined, maybe you're not seeing it, but like that's our YouTube channel. You can watch replays of what we did last week and what we did today that you just missed. Unit 1 is from 4:30 to 5:30. So join us next week at that time and you'll be able to see that stuff. I just sent you, what did I just send you? I just sent you the YouTube channel link. And I'm gonna send you the IG, okay?
Okay, Miss. Thanks.
You can follow us there and enter quizzes to win one-on-one sessions with me. And I'll have a variety of prizes too, because not everybody wants to meet with me one-on-one. I know that. But for the people who do, that's a prize that I'm offering right now. The prize is my time, really, to talk to you about chemistry and to help you with what you need help with. And then we can go from there, of course, okay?
Okay, Miss.
All righty. Well, I'm gonna go ahead and end now, but it was a pleasure having all of you. And just definitely catch up on what we did on the YouTube channel and let me know if you have any specific questions. And tell all your classmates and all your friends to join us next week. Unit 1 is 4:30 to 5:30. Unit 2 is 5:30 to 6:30. And then CXC is from 1 to 2:30. Okay?
Okay, Miss. Will do. Thanks again.
All right. Bye, guys. Have a great week now. Bye, Venita. I hope that was helpful for you. Okay? All right, Venita. Have a great week now. Okay?